We now discuss an inner product on the vector space of n by n real symmetric matrices over the field of real numbers from the section Linear Algebra. We defined an inner product and we will show that it satisfies all the properties of the inner product. The result is, let n belongs to the set of natural numbers n greater than 1. Let V be the vector space of n by n real symmetric matrices over the field of real numbers. Then bracket A comma B defined as trace of the product AB for all A comma B belongs to V is an inner product on V. We will now verify that it satisfies all the properties of an inner product. Let's now recall the definition of an inner product. We have V, a vector space over a field of real numbers or complex numbers. A map that assigns for each ordered pair of vectors u comma v in V a scalar f written as u comma v is called an inner product if it satisfies the following properties. The first property, IP1, inner product, first property, bracket u comma v is equal to v comma u for all u comma v belongs to V when f is the field of real numbers and it is called the symmetry property. And in the case of the field f is the field of complex numbers, then bracket u comma v is equal to the complex conjugate of the bracket v comma u for all u comma v belongs to V when f is the field of complex numbers. This property is called the conjugate symmetry property. IP2 is bracket alpha times the vector u comma v is equal to alpha times bracket u comma v for all uv belongs to V for all alpha belongs to f. IP3 bracket u plus v comma w is equal to bracket u comma w plus bracket v comma w for all uvw belongs to V. These two properties, IP2 and IP3 together, is the linearity in the first slot. The alpha scalar should be there in the first slot only, then only this is true. IP4 bracket v comma v is greater than or equal to 0, non-negative, for all v belongs to V. IP5 bracket v comma v is equal to 0 if and only if V is the zero vector. If those five properties are satisfied for that bracket, then it defines an inner product. We have this result. Result is, let n be a natural number, n greater than 1, and we have V the vector space of n by n real symmetric matrices over the field of real numbers, and the inner product is defined as bracket of A comma B is equal to trace of the product of the matrices AB. For all A comma B belongs to V, we have to show that this defines an inner product on V. So before entering into the proof of it, we first review the properties of the trace of a matrix. We recall the properties. trace of X transpose, a matrix X transpose is equal to trace of X. Trace of the sum X plus Y is equal to trace of X plus trace of Y. And the trace of alpha times X, where alpha is a scalar, is equal to alpha times trace of X. And this is true for all X comma matrices X comma Y belongs to V, for all alpha belongs to R. Agreed. We verify the first property, IP1. Bracket of A comma B is equal to, by definition, trace of the product AB. That is equal to the trace of the transpose of the product AB. And we know the trace of X transpose is equal to trace of X. Therefore, trace of AB is equal to trace of AB, the product whole transpose. That is equal to trace of B transpose A transpose, because AB whole transpose is equal to B transpose A transpose. That is the reversal law. And the trace of B transpose is B, because this V is the vector space of all n by n real symmetric matrices. So B transpose is equal to B, A transpose is equal to A, and that is equal to trace of the product BA. The trace of BA is the bracket B comma A, and that means bracket of A comma B is equal to bracket of B comma A for all AB belongs to V. Thus, the first property of the inner product is satisfied. IP2, the second property, and bracket of alpha A, alpha is a scalar, comma B is equal to trace of alpha A multiplied by B. That is equal to trace of alpha times the product AB. And we have the property trace of alpha X is equal to alpha times trace of X. Therefore, trace of alpha times the product AB is equal to alpha times the trace of AB. And the trace of AB is the bracket A comma B. Therefore, this will be alpha times bracket A comma B, true for all matrices AB belongs to V, for all alpha belongs to R. Now, third property, bracket A plus B comma C is equal to trace of the product A plus B multiplied by C, that is equal to the trace of AC plus BC. We are using distributive law of matrices. And the trace of X plus Y is equal to trace of X plus trace of Y. We'll get trace of AC plus trace of BC. Trace of AC is bracket of A comma C plus trace of BC is bracket of B comma C. Thus, we have proved bracket of A plus B comma C is equal to bracket A comma C plus bracket B comma C, true for all ABC belongs to V. Thus, IP2 and IP3 put together, the linearity in the first lot is proved. To prove IP4, IP5, we take A to be the n by n matrix whose ijth entry is Aij, and B is equal to Bij n by n. Then the product AB is equal to, let us say, capital C, whose ijth entry is Cij, where Cij will be, by definition, sigma k is equal to 1 to n Aik multiplied by Bkj. Yes. Now, the bracket A comma B is equal to trace of the product AB, that is equal to the trace of AB means sigma Cii. Sigma I is equal to 1 to n Cii, and Cij is sigma k is equal to 1 to n Aik Bkj. Therefore, Cii will be, wherever there is j, you write I again. So, you will get sigma sigma k is equal to 1 to n aik into bki. So you got this one. Now sigma I is equal to 1 to n, sigma k is equal to 1 to n aik bki we can write because these are finite summations. So now you take any matrix capital A, we verify the fourth property IP4, bracket A comma A is equal to sigma I is equal to 1 to n, sigma k is equal to 1 to n. In the place of b, bki, you write aki because we have a comma a. Now in the place of b we have a aki. Now for this aki I can write aik. Why? Because A is a symmetric matrix. Because A is a symmetric matrix, then aki, the entry in the kth row ith column is same as the entry in the ith row and kth column. So that will be equal to double summation aik into aik. Aki is equal to aik since A is a symmetric matrix. So that will be double summation I is equal to 1 to n, k is equal to 1 to n, aik square. This is sums of the squares of real numbers. It will be non-negative, greater than or equal to 0 for all a belongs to v. Thus, the fourth property is satisfied. The fifth property, bracket a comma a is equal to 0, if and only if, go back, sigma double summation, sigma I is equal to 1 to n, sigma k is equal to 1, aik square is equal to 0. Sums of squares is equal to 0 implies each entry is equal to 0. This is if and only if aik is 0 for all I comma k. When aik is equal to 0 for all I comma k, the matrix A is the 0 matrix, if and only if A is a 0 matrix. Thus we have proved bracket of A comma A is equal to 0 if and only if the matrix A is a 0 matrix. Thus we have verified the fifth property of the inner product. Thus the bracket of A comma B is equal to trace of AB defines an inner product on V. So it defines an inner product on V. So that is the verification of the properties of the inner product for the given inner product. Agreed. Hence the result. So that's the result what we wanted to prove, and this result is needed, and you can use this result in some of the examples. For instance, there is one question what has appeared in CSIR National Eligibility Test Mathematics on 16th February 2022, and it is from the section B, and wherein you are given the 4 options. In these 4 options, in a previous video I have shown that option 2 is an answer by an elimination method, that is by giving counter examples. Option 1, 3 and 4 cannot be inner products. Thus I have concluded the option 2, that is bracket of A comma B is equal to trace of AB, is the answer for this question. But now that I know by the above result, I know the bracket of A comma B is equal to trace of AB for all A comma B belongs to V is an inner product on V. Therefore, the option 2 is the correct answer for this question. So, therefore, option 2 is the answer in this example, and without, you need not go into searching for the counter examples for options 1, 3 and 4. If you have this result, this is a very standard result, and that is why this result I have proved independently, so that you can use it in future in some discussions related to trace of a matrix and the definition of the inner product. I am sure that you understood the result and the verification of the inner product, and you have also understood how that can be used in this example. If that is the case, I wish you all the best. Thank you.